Hello students, welcome to the IMS GATE Academy. So in this series, we'll continue the instruction pipelining. We have started already instruction pipelining. The 4 sessions already we have taken. This is the part 5 on instruction pipelining. So what was the discussion happened in the last class, the last session? We have started like some control dependency. The control dependency problems, how it is occurs, what are the solutions for the control dependency we have started, right? So now we'll continue this one. So part 5 here the focus goes on control dependency, means solution to the control dependency. The solution to the control dependency, solutions. The various solutions I have started. The first solution which we discussed was what? Multiple pipelines. So multiple pipelines. Multiple pipelines. Then followed by, so what was second one? Second one was reducing the branch penalty, reducing the branch penalty, BP, branch penalty by early deduction, reducing the branch penalty by early deduction of the branch instruction and evaluation of the branch condition, right? The followed by third one, branch slot delay, branch delay slot. So what is a branch delay slot? What we had a discussion on this. In a branch delay slot, because in a reducing the branch penalty means we reduce the branch penalty by 1 clock cycle, means the decode stage we modified, we made much intellectual to decide or to detect the what I can say, it is a branch instruction, and also the generation of the target instruction happen in a decode stage only. So with this one, what is only 1 clock is going to be wasted, only 1 clock is going to be wasted. How we can utilize this 1 clock? So branch delay slot saying that in a compiler time we can insert one instruction called NOP instruction, no operation, which is equivalent to fetching an instruction and flushing out the instruction from the pipeline, so that overhead of the instruction pipeline can be reduced by placing the NOP instruction after every branch instruction. So later they also again useful instruction placed that their branch delay slot can be filled by some independent instructions, so that throughput may be increases. So that was the discussion happened. And the fourth mechanism or fourth technique for dealing with the control dependency is what? Prediction method, prediction. So branch prediction. So branch prediction. So this is even I understand now. Even we want to reduce that one slot also, because one cycle is wasting. The 2-3 method if you see, solution 2 and solution 3 method if you see. So one slot is going to be wasted, or in solution 3 what we were utilizing, but still finding independent instruction, placing into that slot, branch delay slot also quite difficult, because indirect dependency may arises. So that also can be replaced by another mechanism called prediction method. How prediction method works, we'll observe now. So one more thing I would like to say all of you, this practical cases, most of the computer architecture are deployed with what? Prediction method, branch prediction. So the best example if I want to say, Intel Pentium processor also, so what having what? Branch prediction only, through what? Branch prediction only, all conditional hazards have resolved. Let's see how this prediction is going to work, we'll observe. The branch prediction. So the few points I mentioned. So what I'm trying to say, the branch prediction will work on the fetch stage only. So we have to make the fetch stage should I have some knowledge no. So the fetch instruction to be noticed, this is a branch. If the branch is there, then we have to make a prediction whether the branch will take or not, whether branch condition will satisfy or not. So based on that only one of the instruction can be placed after the branch instruction. So what is saying, to reduce the branch penalty further, branch penalty minimum was happening 1. To reduce this branch penalty further, the processor need to anticipate that an instruction being fetched is a branch instruction. At the fetch stage has to be anticipate that the instruction which is fetched by it should be the branch instruction, and also predict the outcome of the branch instruction. So and also predict the outcome to determine which instruction should be fetched in cycle 2. Cycle 2 means what? Next. When the instruction goes for decode stage in the next cycle, should we fetch in sequence instruction or target instruction? That should be decided in the fetch, end of the fetch stage only. So this prediction can be 2, static or dynamic. The static prediction, the fixed prediction, understand. So dynamic prediction changes the based on the previous predictions. So previous, like what history of the branch instruction. The dynamic prediction dynamically changing. Let's observe both of them. So what I'm trying to say, suppose let's take, so what the program is there, program, okay. So this is a program having instruction 1, instruction 2, instruction 3, instruction 4, like this, instruction 8, 9, 10, okay. Observe now. So instruction 2 is a branch instruction, this is a branch instruction, conditional branch. Its target is what? I9, I10, I8, sorry. Branch instruction target is what? I8. Okay, now see. So now with the branch delay slot, what we did, like we have fetched, let's say, so I'm going with this fetching of instruction 1. So I'm considering 4-stage instruction pipeline. So instruction 1 I fetched, the followed by decode, the followed by execute this instruction, store the results. When instruction 1 fetching is over, then we can fetch instruction 2. What is instruction 2? Fetch. Instruction 2 is what? Branch instruction. Instruction 2 is branch instruction. So normally, please observe here, during decode stage only, like we modify the data path, in a decode stage we have to decide, end of the decode stage we have to decide whether sequential instruction to be fetched or target 1. But to reduce the further the penalty, branch penalty, now you have to anticipate here only. In the fetch stage only, the fetch stage itself should anticipate this the fetched instruction branch, as well as we have to determine the which instruction is going to be fetched in the second cycle, means this cycle. Here you have to decide, end of this stage only you have to decide, here only you have to decide, either you have to fetch the target instruction or sequential instruction you have to decide. So sequential instruction, okay. So by applying what? Prediction method. By applying what? Prediction method. Prediction method, okay. By applying the prediction method, you have to decide end of the fetch stage only the next instruction to be as a branch or target or branch sequential instruction. Are you getting my point? I hope you are understanding the internal meaning of what we are trying to do in a prediction. Okay, what we can be done, sir. Now in a fetch stage, when you anticipate this is a branch instruction, immediately some kind of prediction. What is prediction? Very simple. So like I'm discussing the first one. Suppose if I use a static prediction, okay. If I use a static prediction, okay. So static prediction, please understand here how this will work. We'll observe. The prediction means you have to just predict whether you will take the branch or not. So like suppose observe here. Suppose the prediction is there. So I'm taking the prediction condition, okay. So I'm predicting that branch will not take, branch. I'm predicting what? Branch never takes, I'm writing, never takes. BNT means what? What is the meaning? Branch never takes. This is a prediction, branch never takes, never taken or never takes assumption, okay. Suppose I'm making my prediction as a branch never take. When you predict the branch never take, which instruction should execute? Are you getting my point? Suppose I'm saying that this is a branch instruction. It's saying the branch will not take, means what? Which instruction you would run? Sequence instruction only. So now what you can do? If the prediction is branch never take, you have to place what? Next sequential instruction. Yes. So next sequential instruction to be fetched. Next sequential instruction. Next sequential instruction to be fetched here. I hope you are understanding, okay. If the branch prediction is branch never takes, means you have to place, you have to fetch, you have to place. After the branch instruction is what? Sequential instruction. Suppose if the first thing, this is the first and second one. Suppose if the your prediction is branch always takes here. So what is the prediction? So branch always takes. Branch always takes. What is my prediction? Branch will take. You are predicted as a branch will take means what? You have to run target instruction only, you have to fetch it or not. So now see the target instruction. So target, okay, target instruction to be fetched here. So target instruction to be fetched. There are two things need to be understood. Very simple. Two-state machine I can develop. What is the two-state machine? I am making, branch never takes one state number 1. Let's take this as state number 0. Then branch always takes a state number 2. That is a state number 1. Now see now. Whenever branch instruction is fetched, initial state is what? Initial state is a branch never takes. So branch never takes means, please understand, next instruction. This is the next instruction. Please understand. So next instruction is a following up what? Branch. After branch instruction you have to fetch it what? Sequential instruction only. What is the prediction? Branch never takes. Branch never takes my prediction M. So I fetch the branch instruction. I am predicting branch never takes. So that I place what? Sequential instruction only. So now branch has started, fetch, decoded, execution done. End of the execution or end of the store time. So address got generated. So let's take example. Branch taken. Branch taken meaning my prediction is wrong. So then by the time what happened? My sequence instruction got fetched or not? Sequence instruction got fetched. It is jumping to target instruction. That means you have to full pipeline. You have to flush it out. Then fetch the target instruction. Means my prediction is wrong. When the prediction is wrong, the full penalty means, to understand, entire pipeline you flush it out, the target instruction freshly we fetched, right? So now flushing out happen, right? Now full penalty happen. This is the case number 1. Whenever, please, very simple thing I am trying to say, when you predict something, if the prediction is wrong, what happened? Full penalty. Your prediction is right, no penalty. Why, sir? Suppose you predict branch never takes, you predicted, you place sequential instruction running. So targeted is under time, the condition might be false. It is not going to for taking the what target instruction. So by that time already sequential instruction already fetched and decoded, right? So you are benefited only. So no penalty happens. Now see, so now how this will work? The first initial prediction is branch never takes. If my prediction is wrong, I'm jumping to this one. So now prediction value, I'm taking flag value t. So t equal to 0, t equal to 1, I'm marking. So t equal to 0, nothing, branch never takes. T equal to 1, nothing, branch always takes the value. Now see, what I'm saying, if my prediction is wrong, I'm changing the state, t equal to 0, I'm moving here. Okay, I'm here as state 1. Then again, second instruction, again second branch came. Now I'm predicting what? Branch always takes. So I'm predicting what? Branch always takes. Now branch always takes means what you have to place it? Target instruction you have to place it. So this is the target instruction I placed, okay, after the branch. Now see, what is the prediction? Branch always takes. If my prediction is right, so anyway branch target instruction fetch it or not? Yes, you benefited. If suppose my prediction is wrong, then what happens? So the target is, I say I made it, branch will take. No, branch is not taken. So branch is not taken, my prediction is wrong. Then you change the state. Now see. Sorry, the t equal to 1. This is the t equal, why t equal to 1? Branch has taken. Now t equal to 0. Branch, I predicted branch will take, but branch has not taken. So I change the state. Each time, please understand, the static prediction means I'll fix a one state. I'll predict something. If success, I'll change the state. If unsuccess, also I'll change the state. I'll change. Each time I'm changing the state. Sir, how practical will work this one? Let's take, for loop is there. Suppose for loop, I'm taking for loop. I is there, I is repeating from 1 to 10 assumption. Some instructions are there. Okay. So these are the target instructions. These are sequential instructions, right? After this loop, only sequential instruction will be there. Correct or not? After this, only sequential instruction will be there. Correct? Now, so first time. So for loop is a branch. I is repeating 1 to 10. 1 to 10 repeating or not? Initial I equal to 1. We'll test I less than or equal to 10 or not 10. True. So initially my prediction is what? Branch never takes. So that I place the sequential instruction. Okay. Now I equal to 1. 1 less than equal to 10. So condition is true. So branch has taken. So my prediction is wrong or not? So I wasted my full pipeline. Wasted or full pipeline. So I am here now. So now when I equal to 2 becomes, I predicting that branch will take. Are you getting my point? Branch is what? What I am trying to say, branch is taking. What I will do it, branch is taking. Are you getting my point? Are you getting? So branch, so branch is true. Like suppose I predict branch always takes. Branch always takes. Suppose branch has taken. So I equal to 2 also, I less than, I equal to 2 is less than 10, condition is true, branch has taken. So branch has taken nothing but, so target instruction I place, this is a target instruction, success or not? Success, change. Then I'll again come here, I will come back to here, so change the state, okay. So sorry, branch has taken means I have to keep here only. So branch has taken means what? I have to repeat here only, because whenever condition is false, I'll make it. So this also I'm making what? So this is t equal to repeat 0. Now see, when I equal to 2, observe, when I equal to 2, what happens? So condition is true. So branch I predicted what? So target instruction I placed. So my condition is true. When I equal to 3, when I equal to 4, till I equal to 10, what happens? All my conditions are true or not? All my conditions are true or not? Yes or no? So each time whenever my prediction, whenever I made the prediction, so all the time this target instruction only fetched. So now understand, initially when I equal to, so one time only my prediction was wrong, then after that all predictions are right only, correct or not. So last time when I equal to, so last time what happened, when I equal to 10 becomes, I predict that branch will take, so branch will not take, so condition is false, then coming here. So now see, in the worst case, please understand how much my prediction rate would be. Can you guess? In the worst case, in a for loop cases, what happens? Most of the time, initially and last will be the incorrect. Otherwise, the remaining time my prediction is going to be right only. In a worst case, what rate of prediction going to be correct? Can you tell me? Suppose each time changing. Suppose I predicted something, so it's wrong. So second time maybe my right. Third time may be wrong. Like this, if shifting will also happen, minimum can I expect the 50%, 50%. So 50% my predictions are going to be right or wrong. 50% time my prediction is going to be right or wrong. Please think yourself and understand and just comment it. 50% time, so minimum prediction is going to be happen. Even suppose if I take like the if else if condition, if else if condition repeating several times, if else if condition repeating several times, if condition is true one thing, so if condition is false other things, so 50% time we can get it. But especially for loop we may even expect more than this value, correct or not? Are you getting my point? So now here is a two state machines only. What is two states? I am changing from 0 state to 1 state, 1 state to 0 state. So 0 to 1, 1 to 0 I am doing like. So this can be modified. This can be modified. This can be modified to dynamic what prediction? Dynamic prediction case what we do? We'll save the previous previous predictions. Based on the previous predictions, we'll change the current prediction. So that may giving the more efficiency also. More efficiency also. Let's observe that. So so dynamic prediction will observe it. So dynamic prediction will observe. So dynamic predictions, so what we do here, so we'll observe the previous predictions. Based on the previous predictions only we'll do it. How this will happen, observe. So here condition for prediction is condition for prediction. So condition for prediction, please understand, condition for prediction. So what is there? So whenever I'm writing all of you, whenever previous to consecutive predictions are wrong, incorrect, Meaning what is saying that, so this prediction, like condition for prediction to change, like we have to change. When to change the prediction? Very simple. Whenever previous 2 consecutive predictions are incorrect, change the prediction. So then you have to what to say? Then change the prediction. Then change the prediction. Then change the prediction. Then change the prediction. So we need to observe previous 2 consecutive predictions, how the nature of the previous 2 consecutive prediction. Based on that, we have to change the what prediction condition. Observe how we can done. We'll observe here. Now here I am taking the 4 states I am taking. So now flag t value will be 0 or 1. So my 0 indication what? What is 0 indication? So branch never takes. So this what branch always takes the condition. Okay. So now I am taking the 4 states here. Observe the state number 0. Okay. So I'll mark it. State number 0, state number 1, state number 1, state number 2, state number 3. Like, so I'm marking here S0, state 0, S1, S2, S3. Observe. So what this each stage represents, we'll observe clearly. We'll observe what each stage is representing here. So now initial prediction as before, also branch never takes my prediction. Branch never takes my prediction. Okay, please observe. So if the branch never takes a prediction, what you have to place is next is instruction. Next means if I write next means you write next is sequential instruction only. So next is sequential instruction need to be fetched. Let's take as assumption, suppose my prediction is wrong. So I predict a branch never takes, prediction is wrong, now branch has taken. So taken means you change the state, So t equal to what? What I predicted? Branch. So branch will not take, so branch has taken. So now you are at here. So again second time also I will predict what? Branch never takes only. So what I said, you 2 consecutive wrong, then you change the prediction, otherwise you continue that only. So again second time, one time I wrong, right? My prediction one time wrong. Second time again predict branch never takes. Again taken, assume that. So taken meaning what? So t equal to 0. Now see, so sorry, t equal to 1. So t equal to 1, observe. So I predict a branch never takes, so but taken. So now again I am predicting that branch never takes. So next sequential instruction placed here. So my prediction is wrong. 2 times full pipeline is wasted. Full pipeline wasted or not? Then observe now. So now whenever it is taken, right, now I am changing the condition, branch always takes here. So there are 2 previous conditions were wrong. So I change the condition, branch now I will takes. I am saying the branch will takes. So I am predicting the branch will take. Suppose if it is taken, branch is taken, assume that. I have to repeat here only. So branch t equal to 1 here, repeat. So n number of times branch has taken, my target instruction I place here. Here I have to place what? Which instruction ma? You have to place which instruction you have to place it? Target instruction you have to place it, target instruction. You predict a branch always takes, you place a target instruction. If the prediction is right, you repeat this state only. Clear? Clear all of you? Suppose your prediction, you predicted that branch always takes, you place a target instruction, your prediction is wrong. Prediction is wrong, nothing but you predicted what? You predict branch will not take, branch will take. Branch will take you predicted, but branch has not taken. So now, so change the prediction. Again second time also I am predicting branch always takes here. The first prediction was branch always takes, I place a target instruction, my prediction is wrong. So branch has not taken. Now I change, so now again I am predicting what branch always takes. So I place a target instruction here. So target instruction I place, branch has not taken. So the second time also wrong. So t equal to what? 0. Branch has not taken. So now see, so I change the prediction or not now? Now see, 2 times I predicted branch always takes, but not taken. So 2 consecutive fails happen, then I change what? Branch never takes. So suppose if the branch never takes, predicted, I place next sequence instruction. If my prediction is right, you are in this state only. So you repeat this state, t equal to 0. Sir, if you are in this state, suppose your prediction is right, then you will come, so you have to come back here, t equal to 0, right? Sir, you are in this state, you predicted a branch always takes, but taken condition is true, sir. then you will come back to here. So T equal to 1. So I hope you understand this one. So now this one, please observe this. So I'm marking as a stars. I'm marking these two states are star. So the stars indication are, you understand here, these are the strong states. Strong state. What is the meaning of strong state? Strong state meaning we're changing the changing the prediction. So if I'm predicting what branch never takes, I observe next to 2 consecutive predictions. If 2 consecutive predictions are wrong, I'm changing the prediction. See, I change the prediction to branch always takes. Again, observe the 2 consecutive predictions wrong, I'm changing the prediction. So these 2 states are dynamic states or strong state, which will change the prediction based on the previous history only. What is the previous history? See, 2 consecutive predictions are wrong, I'm changing. 2 consecutive predictions are wrong, I'm changing the prediction. So now let's work out the for loops. Let's work with the for loop here. Suppose for loop is repeating for 100 times. When I equal to 1 to 100, assume that I equal to 1. What is initial my prediction? Branch never takes. So that I place sequential instruction. But when I equal to 1, I less than 100, condition is to branch has taken. So my condition is false. Full pipeline penalty. Second time, I equal to 2 become, again branch started execution. I'll predict branch never takes. I place the sequential instruction. When I equal to 2, 2 is less than 100. Condition is true. Condition is true or not? Condition is true. So it has taken the branch. So second time also my prediction is wrong. Now I'm changing the prediction. Branch always takes. I place the target instruction. I equal to 3. 3 less than 100. Condition is true? Yes, true. It will change. Jump to target instruction? Yes. I place target? Yes. So third time my prediction is going to be right. Now fourth time I equal to 4? Yes, I predict branch will take. Taken. I equal to 5? Yes, yes. Still I equal to 100. 100 when I become 100, 100 less than 100 is not true. So branch you predicted takes, but branch has not taken. So now my condition is false. My prediction is wrong. See, I equal to 3 to I equal to 99. I equal to 100 till 100, right? Till 100. I'm right or wrong? I'm right or wrong? Yes. So this many predictions happen, ma. So this produces a maximum throughput. Maximum throughput means understand. This gives a more efficiency means understand. So the accuracy of the any cases, accuracy of the prediction rate is more than 85%, 85 to 90% it is giving. So now the practical cases we are implementing to deal with the branch type like conditional hazards or conditional dependencies by using dynamic prediction mechanism, right? The 4-state machine, the 2 flip-flops. So 2 flip-flops enough to implement this one. So that will decide which instruction to be fetched in the next cycle. Yes, I hope you understand the concepts. So this is how we deal with the control dependency problems. So because this is giving more prediction rate compared to what static one. This is giving the more prediction rate compared to static prediction. Chalo, we'll move. So we'll move to the third problem. What is the third problem? Structural dependency. We'll move to third problem, structural dependency or structural hazard. So this generally this problem arises due to limited resources. Due to limited resources. So what are the limited resources, sir? Observe. Suppose I'm using the 4-stage instruction pipeline. So instruction 1 I'm fetching, fetch instruction. Okay, fetch. So I'm fetching instruction 1, then followed by decode this instruction, followed by execute, store the results. Then once fetching is over, another instruction I'll put instruction 2, fetch, instruction fetch, instruction decode, execute, store the results here. The followed by instruction I3, fetch I3, decode this instruction, execute this instruction, store the results. Let's take each instruction, take 1 clock cycle, 1, 2, 3, this is 4, this is 5. Observe clearly. Now instruction, sorry. So now instruction 4 will be fetched here. Instruction 4 fetched. Here is decode, then execute and store. So it will happen at store 6 o'clock. Observe carefully. How structural hazards occurs, observe. Now see. Here is what is happening here. What is happening here? Please observe. What is happening? You are fetching, right? You are fetching. Okay. So fetching. What is happening? Store. Okay. Now What is the meaning of store? Can you tell me what is the meaning of store? Store means, please understand, some CPU registers, let's say register to memory access, right? Results, some register to you have to store in memory, right? What the fetch is happening here? What is the meaning of fetch? So we'll take an address from program counter, we'll go to memory. So memory, get the instruction. So both required memory access or not. Storing of a results into memory, fetching of instruction from the memory required, accessing the memory or not. Say sir, no. If single bus architecture is there, if the single bus architecture is there, so these two stages cannot overlap. Please observe. These two stages cannot overlap at the same time. Same time you want to go for storing the results into memory, same time it's going to be fetch instruction from the memory. Single bus architecture, this is not possible. That's what limited resource may cause as what structural dependency. This is one problem. Another problem you observe here. Another problem observe. Here is what is happening? Execution. Here is happening fetch. So execution required ALU or not? Yes or no? Execution required ALU. Now end of the fetch instruction, ALU required for incrementing the program counter. Do you agree? To increment the program counter, arithmetic logical unit is required or not? To execute the instruction, arithmetic logical unit is required or not? Now understand. Instruction I1 executing here, instruction I3 fetching is over, we want to increment the program counter. So again, so these two stages cannot be overlapped. Reason? Single port ALU unit is there, single ALU component is there, hardware is there. Execution of one instruction, incrementation of the PC of another instruction not possible at the same time. Hence we need what? Two ALUs. Hence we need two separate buses for fetching of instruction and storing of instruction. In the modern architecture, if you see, level 2 cache having the divide into two things, I cache and D cache. So instruction can be fetched from I cache and data can be stored in the D cache. So this can happen parallel because two systems, two buses are there for level 2 cache, like I cache and D cache. That how modern architectures are going to be resolved by duplicating the resources. I hope this is clear. The solution to the structural dependency is very simple. Required to like duplicate the hardware components so that we can implement the instruction pipeline more effectively. I hope you understand the problem. I hope you understand the solution. The solution is what? Duplication of resource only. That's it. I hope this is clear. Right? So what are the things we have seen? What are things we have seen? Prediction. So this prediction can be static prediction. It can be dynamic prediction. Static prediction, what I said, just two states are there. You are at branch, never it takes is a prediction. You place the sequence instruction. If it is branches, like if the branch is true, you are in same state. If the branch is false, you are going to change the another state. You are going to change the another state. Suppose you predict branch never takes, but it taken. You went to here, then again you predict branch always takes place the target instruction. If it is taken, then you are in another state. If it is not taken, then you have to change the state. Change the state. Yes, I hope you understand. So note of it this thing so that we'll move the problem solving now. So the dynamic prediction is the 4-state model where I shown the clearly where to change the prediction. So then structural dependence we have seen. So let's move on to the problem solving. So this question, like we have solved in the previous session. Please go and verify. Answer for this question is what? B, 165 nanosecond required to complete this program. Chalo, we'll move to another question. The question number 10 I marked because previous states. So like previous consecutive sessions we have taken some questions from the pipeline. So that's the reason I sequentially maintain the question numbers here from, so like hazards, like, so what this question says, question number 10, which was asked in 2000, sorry, this is asked in GATE 2000. So GATE 2000, okay, this is asked in GATE 2000 paper for 2 marks. The instruction pipeline support overlapping of all the instruction except the conditional branch instructions. The third stage of the 5-stage instruction pipeline is capable of evaluating the condition and providing the target address of the conditional branch instruction. The pipeline will not fetch the target conditional branch instruction until the branch outcome is known. Until the branch outcome is known, it won't fetch any instruction after the branch. That's it. Who is the generator? Who is generating the target address? Third stage of the 5-stage instruction pipeline, correct? The pipeline is operated with 1 gigahertz clock. 20% of 10 power of 6 instructions. 20% of 10 power of 6 means 1 million instruction. 20% of 1 million instructions are conditional branches. How much time is required to implement this above program? In milliseconds they are asking. So observe, there are 1 million instructions are there. 1 million instructions are there. So 5-stage instruction pipeline. So 5-stage instruction pipeline. Okay, now understand stage 1, stage 2, stage 3, stage 4, stage 5. Who is the address generator? This one is the like. So end of the third stage will get the target address. Target address. Target address. Okay, now. And also said, whenever branch instruction you fetch, decode, end of the execution stage only, end of the third stage only will get the outcome. And also one more point said, so no instruction being fetched until, sorry, target instruction is not fetched until branch outcome is known. So till the branch outcome is known, so no instruction being not fetched. Means end of the third stage only will get, suppose the condition is true. If the condition is true, please understand, if the condition is true, then we'll get a target address we can fetch. Now suppose third stage is address generated, how many stalls are going to be wasted? Can you tell me? Can you tell me? So third stage is a address generator. Now how many stalls going to be happen? I said you kth stage instruction pipeline. Suppose some instruction pipeline, kth stage is address generator, k minus 1 stalls happen. Minimum k minus 1 stalls happen. I hope this line is clear. I hope this line is clear. So what you can also read, they said here, third stage of the 5-stage instruction pipeline is capable of evaluating the condition, providing the target address of the conditional branch instruction. The pipeline will not fetch the target of conditional branch instruction until the branch outcome is known. So now see, here end of this only address will come, then only it will fetch. Other sequence instruction might be fetched, we need to flush it out. How many stalls are going to have wasted? 3 or 2. So now it's simple. How to know? Whatever the stage is providing, that stage minus 1. So 3 minus 1 is 2 stalls are going to be wasted. 2 stalls are going to be wasted. How, sir? Let's take example. Let's take, I'm taking example 1. I1, I2, okay. I3 are there. Then I9 is a branch. So target, this is a branch instruction. So this is a branch instruction. Target is I9 assumption. How this is going to be executed? 5 stages, right? So I1 fetch. So fetch means stage 1 work. Stage 1. Okay, stage 1 work. Followed by stage 2. Followed by stage 3. Stage 4. Stage 5. Correct. Then you understand. So I2. S1. S2. S3 here. Okay. So by that time what happens? I3. S1. S2 work. Right. So by that time what happened? Instruction I4. So this is what S1 work over. Now see, end of the clock we got address. Then end of the clock address got right. Now you are going to fetch your target. What is the target instruction? I9. So now I9 going to be fetched here. I9 going to fetch. Now see, this means now to flush it out or not? So this instruction need to be flushed out or not? When you flush it out, how many stalls are wasted? Maximum 2 or not? So 2 stalls are wasted. So generalization, every time you cannot draw the timing diagram and get the how many clock cycles are wasted. Simple thing, you look at the whatever number of pipeline stages given. Suppose kth stage is the address generator. Kth stage is the address generator. Now k minus 1 will be the stalls. What is the kth stage here? S3 is address generator. S3, 3 minus 1. So 2 stalls are going to be wasted. This way you can understand. Now, so we need to find out the time for program, right? Time for program. So I am suggesting you go with a clock per instruction. Clock per instruction average. So naturally, ideal cases, please understand, ideal case what clock per instruction, the pipeline will be what? 1 clock cycle only, right? 1 clock. But due to dependency, some delta clocks extra will be there. I was discussing in early classes, like no, you go and refer session number 1 or 2, you will come to know what is a delta. Either session number 1 or session number 2, I discussed what is the meaning of delta. Again, I am clearing, you better think you can go and watch this thing. What is the meaning I am telling you? If all independent instructions are there, if you run in a pipeline, we will take one instruction, 1 clock on each instruction. But if there is a dependency, would be a data dependency or would be a control dependency. Due to this dependency, some stalls will increase. How much stall? Delta stall. Now observe here. So 1 plus, what is the delta? Delta means, please observe here. They said, 20% of instructions are branch instruction. 20% of instructions are branch. I am writing delta word. So 20% instructions are branch. Okay. Due to this branch instruction, how much extra stalls are going to be happen? How many extra stalls are happening? Tell me. How many happening? 2 stalls or not? Each branch instruction, 2 stalls are going to be wasted. Yes or no, all of you? Each branch instruction taking 2 stalls extra or not? Because you are jumping target, now you have to flush it out of the pipeline. Like 20% of 1 million instructions are there, those one will wasted. So now simply I am calculating for 1 instruction, later you can multiply total number of instructions. So 2 stalls are wasted. So this value giving how much? So 1.4 clock cycles. So 1.4 clock cycle, correct or not? 1.4 clock cycles. Now time for program. So time for program equal to how many instructions are there? 10 power of 6 instruction. Each instruction average taking 1.4 clocks. Yes or no? 1.4 clocks. So this is the multiplication, understand? Okay. So 10 power of 6 instructions are there. Each instruction take 1.4 clocks. Why 1.4? Naturally it should take 1 only, but due to this dependency 0.4 extra each instruction taking. Now, but they are asking time, right? 10 power of 6 into 1.4 into clock period. So clock time we need to find. Clock time depends on clock period. What is the clock period? They said 1 gigahertz. Always remember, friends, all of you, try to remember the point, all of you. So time for the clock time, right? Time for clock will be reciprocal to the clock period. Or if you want to find out the clock period or clock rate, it is reciprocal to the time, clock cycle time. So now see, so now clock, we need time, TC value we need. TC means what? Clock time. So that 10 power of 6 into, so 1.4 into TC value will be 1 by clock rate. What is clock rate? 1 by 1 gigahertz, they said. So 1 by 1 gigahertz. Gigahertz, if you send upside, it becomes nanoseconds. Now please understand. So 10 power of 6 into, so 1.4 into, so 10 power of minus, so giga, 9 means 9 only, right? So nanoseconds, can I write it or not? So this is seconds. Otherwise you understand this I can write it. So this I can write it 10 power of minus 6 milliseconds I can write it. Because they asked in the unit. What is the unit they asked? Dash in milliseconds only they asked, right? They asked in milliseconds only. So you can also check it. They give 1 gigahertz only, 1 gigahertz only. So 1 gigahertz only. So properly, if you want to me write it this one, so let me write properly. So what I am trying to say, so time for program. So time for program equal to 10 power of 6 instructions, 1.4 into 1 by 1 gigahertz, right? So this I can write 10 power of 6 into 1.4 divided by, so 1 giga means 10 power of 9 hertz. Can I write it or not? 1 by hertz, can I write it? Now also understand here. So 10 power of 6 into 1.4 into what I'll write it? If you send upside, so 10 power of, are you getting my point? So what I can write it? 10 power of minus 9. So like otherwise you understand what I will do it. So 10 power of minus 9 seconds happens now. Please observe, because 1 by edge becomes seconds, because hertz becomes seconds here. So now this value, how much it will be? This 1.4 divided by 3. So 1 by 10,000. 1 by 10,000 will write 1 by 1000. Sorry, 1 by 10 power 3. 1 by 10 power 3. 1 by 10 power 3, or other way you understand, this will be, so 10 power minus 3 seconds. Okay. So 10 power minus 3 seconds, 1 point. So 10 power minus 3 seconds, 10 power minus 3 seconds, nothing but 1 millisecond. So 1.4 millisecond is answer. So range is 1.4 to 1.4, unit already given milliseconds, right? So this way you can answer it. In this way you can answer it. Clear? Chalo, we'll see another question. This question was asked in GATE 2014, set number 3, 2 marks question they asked. So question is little lengthy, but answer is easy. Always do remember, dear students, from the computer organization, generally or many times happens the questions are lengthy. If the question is lengthy, please understand solution will be easy only. When the questions are small only, there's little difficulty will be there. Because most of the time we spend for reading the question understanding. If suppose, please, if you are in pleasant mode, if you read properly question, if you understand the question, answer will be easy. And suppose unpleasant mode, if you read this question, see now 2 slides happen, no? 1.5 slide is there, question is 1.5 slide is there, right? So if you are not reading properly, if you are not understanding properly question, so answering question becomes difficult. That's only. So most of the times happen in COA, question seems to be lengthy because so much information they will give it. But some information will come because answer is in part of the question only. Answer is part of the question, nothing but the few things need to be done, like no substitution only required, so that you will get an answer. So patiently you observe the question, what the question is talking about. An instruction pipeline has 5 stages. So read like no, if you already you have a notes, rough notes, right? So read and few things, given thing you write down also parallelly, so that the later part becomes easy. So now let me mark it as per here. Like they said 5-stage instruction pipeline. I am reading line by line. I am marking also 5-stage instruction pipeline. Can you tell me what are the stages here? What are the stages? What are the stages? Instruction fetch, instruction decode, and register fetch. Instruction fetch. Second one is instruction decode or register fetch. Instruction execution, memory access, register write back is there. I am marking now. I am marking just. So instruction fetch, first one, instruction decode and register fetch. This means they said like this, comma, execute this instruction, execute only, execute, memory access is there, memory access. So memory access and write back is there, register write back is there. 1, 2, 3, 4, 5. With the stage latencies are 1 nanosecond, 2.2 nanosecond, 2 nanosecond, 1 nanosecond, 0.7 nanosecond respectively. The stage delay is also given. What is stage 1, 2.2, 2, 1 point. So 1 nanosecond. This is what? 2.2 nanoseconds. This is 1 nanosecond. Sorry. So let me check it. 1, 2.2, 2 nanosecond. This is execution is 2 nanosecond. This is 1 nanosecond. This is 0.75 nanosecond. This is given thing. Clear. Next. So N stands for nanosecond. The gain, to gain in terms of frequency, the designer have decided to split the IDR, instruction decode register fetch stage, into 3 stages. Okay, one is ID, register F1, register for fetch 2. Each latency divided by 2.2 divided by 3 nanosecond. Also, execution stage is split into 2 stages, execution 1, execution 2. Each latency 1 nanosecond. The new design has total of 8 pipeline stages. See now, some stages are splitted, so that many stages happen. They said out clearly, new pipeline having how many? 8 stages are there. So now also another information, the program has 20% branch instruction. They said again 20% branch instructions are there, which execute in a execution stage. So branch instructions are executing which stage? EX stage, and produce the next instruction pointer at the end of the execution stage in the old design, and at the end of the execution 2 stage in the new design. Very clearly mentioned now, see. See, the old pipeline means 5 stages are there, right? In that execution stage producing the target address. In the new pipeline, execution 2, second stage producing the address of the target instruction. The instruction fetch stage stall after the fetch branch instruction until the next instruction pointer is compared. Again, same line, they are saying that. So, the target address instruction, instruction fetch stage stalls C after fetching a branch instruction until the next instruction pointer is computed. After the branch instruction, no instruction is fetched until the branch outcome comes. So, penalty will be there. All instruction other than the branch instruction have average clock per instruction is 1. Other than branch instruction, how many clocks? Only 1 clock for each instruction, average. But due to branch instruction, it will take more also. So, both are designed. Execution times of this program on the old design and new designs are P and Q. Nanosecond respect to the value of P by Q they are asking. Very simple thing. Look at the point. This is a 5-stage instruction pipeline. Now, what they made? So, this stage split it into 3 stages, right? This stage split into 3 stages. What they said? One is instruction decode, register fetch 1, register fetch 2. Now, this is divided into how many stages? 2 stages. One is execution stage 1, execution 2. So, now getting my point. So, remaining same only. So, now here is IF will be there, IF instruction fetch. Here is memory will be there, memory will be there. So, write back will be there. So, latency if you see, this time is 1 nanosecond, this time is going to be, so what is the this time? So, 2.2 by 3. So, this is going to be 1 nanosecond, this also going to be 1 nanosecond, this also going to be 1 nanosecond, this is 0.75, no change here. Now, new pipeline, this is a new pipeline, right? New pipeline having how many stages? 8 stages. 8 stage instruction pipeline became. Old one, how many pipelines are there? 5 stages are there. So, times also no. So, this is clear, right? What they are asking? Branch instruction, they are running some instruction running in a 2 pipeline. And in this instruction, 20% instructions are branch instructions only. Now, branch delay need to be computed. Now, one information you have to understand. In this case, the branch instructions are evaluated by which one? Execution stage here. So, this produce a target address. In a new design, who is going to generate the target address? Execution stage is going to generate the target address. Now, tell me how much would be the branch penalty in this case? All of you, please pause the video for a while, think yourself and comment it, all of you. Tell me how much penalty happened in old design, how much penalty will happen in new design. Meaning, when the, so what is it? After instruction fetch, stalls will be the until what? Branch outcomes comes. What are the outcomes? End of the stage only will come to know branch is satisfied, it will jump for a target. If branch is not satisfied, it will fetch a sequential instruction. But it is stalling till this stage. What is stage number? Stage number 1, stage number 2, stage number 3. So, third stage generator right now, how many stalls happen for this one? Is it not 2 stalls? Yes or no? 2 stalls or not? Yes. For the new design, stage number how much? 1, 2, 3, 4, 5, 6. So, 6th stage is an address generator, means 6 minus 1. In this case, how many stalls will happen? The 5 stalls will happen. This is information we observed. Here are 2 stalls, here 5 stalls. Yes. So, now look this here. So, now first of all, clock per instruction. For P is what? Old design. Okay. For get the time for one instruction. Then, so are they given a number of instruction? No, you will take for one instruction better. So, this is a clock per instruction. So, now P design, right? I am making P is the design. So, clock per instruction. So, generally it will take 1 clock only, right? Generally what? All other than branch instruction will take 1 clock cycle only. So, 20% instructions are branch. So, which take how many stalls? Old design what? 2 stalls or not? 2 stalls happen. So, this means what? How much this value is? So, 1.4 clocks. So, 1.4 clocks. Clear all of you? Now, how to get the clock time? Yes, how to get the clock time? TP. How to get the clock time TP? Yes, ma. So, TP, so in this case, clock period not given, but stages delay given. How to take, whenever different stage delays are there, how to take the cycle time of the pipeline? Many times I discussed here. So that is very simple. Maximum of stage delay. Maximum of stage delay plus a register or buffer overhead. So register or buffer overhead. What is the maximum stage delay? 2.2 nanoseconds. So buffer delays, are they given buffer delay? I think 0 only. Buffer delay, we check it. Are they given in buffer delay? Also execution stage. They said register write back latency 1 nanosecond respectively, that to gain. So nowhere they mention, I think, for what I can say, the interstage buffers. So that is considered to be 0 only. The considered to be 0. Now this value is going to be 1.4 into 2.2 nanosecond. You multiply, what the answer it will give? What the answer will give? Similarly, Q is what? New design. So here clock per instruction we can calculate 1 plus 20% branch instruction. But incurring how many stalls happen here? How many stalls are happening? 5 stalls. So this value gives how much? 1.5. This is 2 clock cycles. 2 clock cycles. Now in this case, so pipeline time here, what cycle time of this pipeline, 8-stage pipeline, will maximum stage, what is the maximum stage delay? Will be 1 nanosecond only. So 1 nanosecond. So this is going to be 2 nanoseconds. This is going to be 2 nanoseconds. So what about this value? So 1.4 into 2.2. So 1.4 into 1.4 into 2.2. This gives 3.08. They are giving 3.08. So now what is they are asking here? What they are asking? P by Q value only, right? P by Q only. Yes or no? P by Q. So now 3.08 divided by 2. This is going to 1.54. Sorry, how much it will be? 54 only, right? So 3.08 divided by 2. 1.5. Yes, this is correct. 1.54 is the right answer for this question. So now just you look at what difficulty is there now. 5 stage. I spread in many stages. So stage delay, maximum delay, stage delay here. So cycle time pipeline will be maximum stage delays. Here also you can get it. Now what we know, normal instruction will take 1 clock cycle. Branch instruction will take how many extra? 2 clock cycle for whole design. That's it I did. 1 plus 2% of 20% of this one. New design, what happens? Normal instruction will take 1 clock cycle, but branch will take 5 clock cycles. So we got 2 nanoseconds divided, that's it. Question is lengthy. Question is lengthy, right? Question is lengthy. But answer is simple only, ma. I hope you understand. This 2 marks question. So now let's look at another question. Let's look at the another question, ma. What the question says here? Consider a pipeline of 4 stages. 4 stages. In this pipeline, there are 40% of the unconditional branch instruction whose target is known at the end of the second stage only. Unconditional branch, this is case. And rest instructions are normal instruction. What are normal instructions? Independent instruction means you understand. Normal instruction means independent. Here unconditional branch, how many? 40% are there, 60% normal only. There is no penalty for the normal instructions, meaning independent instruction will take 1 clock. That meaning the cycle time for a pipeline processor is 50 nanosecond here. Cycle time means what? Generally will take now, whenever different delays are, maximum delay will take. But all the stages are same, only 50 nanoseconds. Or you understand, one of the stages may taking the highest delay. One of the stage taking highest delay, 50 nanosecond. Calculate the throughput. Calculate the throughput in MIPS per, MIPS. What MIPS? Million instruction per second, correct up to 3 decimal places. Correct up to 3 decimal. But in this case, they are not asking speed of factor. They are asking what? Throughput of the pipeline. Throughput of the pipeline means how many instructions are executed per second. They said no, million instruction per second need to be calculated. First of all, get the clock per instruction. Get the clock per instruction average. As we know, normal instruction will take only 1. But there are 40% unconditional branch instruction which incur how many stalls? How many stalls incur? How to understand, sir? Second stage is address generator only. End of the second stage we will get. How many stages are? 4 stage. Second is stage. I said a kth stage generating k minus 1 is a stall. Now, so second stage nothing but 1 stall only, right? 1 stall only. So this is 1 plus So what value is going to be happen? So 1.4 clocks, yes or no? 1.4 clocks, right? Clock per instruction 1.4. What is the clock period they given? 50 nanosecond they given. So this is going to how much? 70 nanoseconds, yes or no? Now one instruction average take how much? 70 nanoseconds. This meaning please understand. One instruction takes how much? 70 nanoseconds. But what is the throughput? 1 second, how many instructions will execute? So 1 second time if I give it, how many instructions will execute? That is a throughput only. So that can be done 1 second instruction by 70, 1 by 70 nanoseconds. So 1 by what we can mark it? Observe here. This I can mark it like 1 by 70 nanosecond, 10 power of minus 9 seconds. Can I write it? Send upside 1000 by 70 into 10 power of 6. So 10 power of minus 9, send upside 10 power plus 9 became 1000 I written 10 power of 6. Now see 10 power of 6 instructions. Upside instruction were there, right? Per second, instructions per second. Now this value 0, 0 cancel. How much? 100 by 70, 100 by 7. 100 by 7 how much value? Hundred by 7 is what? 14.285. So 14.285 million instruction per second. They said up to 3 decimal places, right? 3 decimal places. The range. What is the range? 14.285. 285. Yes or no? So any round of things? This is 100 by 7. So 2857, 56, 8586 also can mark it to 14.286. So this is a range of this one. You can understand more. So I hope you understand how to calculate this throughput thing here. Fine. Chalo, we'll move to another question. Now see the question. Question number 13. This was asked in 2021 paper, session number 2 for 2 marks. Observe. Consider a pipelined processor with 5 stages. The stages are instruction fetch, instruction decode, execute, memory access, write back. Each stage of the pipeline except execution stage. Each stage of pipeline except execution stage take 1 clock cycle only. Other than execution, all stages are taking 1 clock only. Assume that instruction decode stage merely decode the instruction and register read is performed in the execution stage only. Yearly mention decode stage only determine the instruction only, but operand fetch happens in execution stage they mentioned here. The execution stage take 1 clock cycle for addition instruction and 2 clock cycle for multiplication instruction. Please observe, other than execution stage, all stages are taking 1 clock cycle only, but execution stage is taking 1 clock for multiplication, 1 clock for addition, 2 clocks for multiplication. Clear? Ignore the pipeline register latencies. Consider the following sequence of 8 instructions are there: addition, multiplication, addition, multiplication, addition, multiplication, addition, multiplication. There are 8 sequence of instructions they did. Fine. Assume that every multiplication instruction data dependent on the addition instruction just before it. Multiplication is depends on addition, and every addition instruction except the first addition is data dependent on the multiplication instruction just before it. So now see, multiplication depends on addition, addition depends on multiplication. This is a data dependency problem. The speed up is defined as follows. Speed up, how they define? Speed of execution time without operand forwarding divided by execution time with operand forwarding. The speed of achieved in executing the given instruction sequence on the pipeline processor round up to 2 decimal places dash. They are asking simply speed of factor. Now here a speed of factor is not comparison to the non-pipeline to pipeline. The speed of factor is comparison to what? Without operand forwarding, with operand forwarding in this pipeline. So we have discussed our operand forwarding is a solution to the data dependency problem. They are testing if I use operand forwarding, how much this is effectively working than the non-operating forming mechanism. Chalo, we'll run. So first you run. So like how many stages are there? How many? 5 stages? Just 5 stages. What are the stages? Instruction fetch, instruction decode, execute, memory access, write back, right? So 5 stages are there. 5 stages instruction pipeline. Instruction fetch, instruction decode, execute, memory and write back. Okay, write back. All stages will take one clock except execution. Execution will take addition, for addition of one clock, for multiplication 2 clocks it is taking. Correct or not? So let us run the instruction. What is instruction 1? Addition. Addition only. Addition followed by multiplication, addition, like this is there, right? Addition. So instruction 1, addition. So instruction addition. Okay, you have to fetch. Okay, fetch. Instruction fetch. How many clocks taking? 1 clock, sir. 1 clock. Instruction decode. Also taking 1 clock too. Execute this instruction. Addition, since it is a addition, so execution also will take 1 clock only. Execution also will take 1 clock only. So memory access. Also 1 clock. Clock number 3, clock number 4. Then write back. Write back. Clock number 5. Clock number 5. Clear? Now, whenever instruction I1 fetching is over, then I can use this fetching of a second instruction. What is the name of the second instruction? Multiplication. Instruction I2 multiplication. So instruction fetch. Then instruction decode happens here. Operand fetch will happen where? Execution stage only, they said. So execution means execution stage and operand fetch, execution will happen, they said. We can decode only, just merely decoding happen, determining will happen, operand fetch happen in the execution stage. Now can I execute here? They said very clearly, instruction I2 depends on I1, meaning you understand. Execution stage I2 required operands. The operand will be available end of this stage only. Depends on that, nothing but results are available end of the 5th clock. Meaning you cannot run here. This stalls only. Stalls only. How many stalls happen? 2 stalls. Now here, please observe. Here you could execution can happen. Because why? In execution stage, operand we have to fetch and execute it. Operands are depends on previous instruction. So when that operand is going to be available, that will be available end of the 5th clock only. Are you getting my point? In data, see now I discussed the session number 3. In the session number 3, operand forward mechanism I discussed with examples also. Please go and observe how we are depends on instruction, how we are forwarding also. But without forwarding, right? We are not forwarding. Without forwarding, I am writing. So stalls I am making here. So clock number 6. Now see, multiplication record how many clock cycles? 2 clock cycles. 2 clock cycle. Okay, 7. Then what happens here? Then memory access. Memory access, then write back. Clock number 6, 7, 8, 9 happens. 9 happens. Fine. Now followed by next. So instruction fetch. Here instruction fetch I'll do. Instruction fetch. Instruction fetch. Which instruction ma? Instruction I3. What is instruction I3? Addition. Instruction fetch. Then instruction decode will happen in this clock. Now see. So can I do execution? No. Because here is execution. But after can I do execution? No. Because addition also depends on multiplication only. So this operand is available end of the clock only. 1, 2, 3, 4. So this many stalls happen. Now here execution can be done. Here is execution can be done. Addition how many will take, sir? Only 1 clock. So clock number 10 you understand. So then memory access, then write back. So then write back or not? So 11, 12, right? So 12th clock, right? So 12th clocks. What is the observation? First instruction takes 5 clocks. After that multiplication taken extra how many? 4 clocks. After that we run addition. How many clocks extra taken? 3, 10, 11, 12. So now is it required to draw the entire timing diagram? So can I generalize or not? What is generalization? Observe generalization. So now see number of clocks, okay? So I am making now number of clocks here, clocks only, clocks I am marking. Otherwise, you understand. So without operand forwarding, right? So clocks. So without operand forwarding. So first instruction taken 5 clocks. Yes or no? 5 clocks only. You see 5 clocks. Then second instruction, this instruction I1 taken 4 clocks extra. Yes or no? 4 clock extra. Third instruction taken 3 clock extra. This is I2. This is I3. So can I mark I4? How many? Multiplication will take 4. Then I5 will mark 3. I6 will mark 4. Plus I7 will mark 3. Plus I8 will mark 4. Yes or no? Now add it. What the value is giving? What is the value giving? So understand this 1, 2, 3. Otherwise understand 5 plus 4, 9. So otherwise this is 7, right? 7, 12, 14, 21, 21 plus 4, 25, 30. 30 clock cycle required. 30 clock cycle required. Now need to find out the number of clock cycle required with operand forwarding. So did you remember I given a tabular form? Did you remember I given a tabular form? Use a tabular form, count it. Otherwise you can also draw the timing diagram. Well, no problem. You can draw the timing diagram also. Suppose if I want to draw the timing diagram, observe now. So I am applying with operand forwarding. Operand forwarding. With operand forwarding. Instruction I1. Okay. So you have to fetch instruction I1, instruction fetch, instruction decode, yes, execute instruction. That's addition taking 1 clock cycle only, then memory access, then write back. What is the clock number? 1, 2, 3, 4, 5 only. Now see. So instruction I2. What is instruction I2? Multiplication. So instruction fetch. So I can do instruction decode. Now execution. Can I do execution here? Operands required. General operands are available end of the 4th clock, 5th clock only. But operand forwarding can be done. So what happens? End of this execution stage only. So operand fetch happen, execution happen. End of the execution stage, results available here. Results available here only. So I can forward here. So you can execute this instruction. Execution required stage, how many clocks? 2 clocks for multiplication, right? Yes, forward happened. Then here I'll do memory access, then followed by, so write back. So clock number 6 and 7, right? So then followed by, next one is what? So next is what? Addition. So addition, instruction I3, instruction fetch, instruction decode will happen here. So can I do execution? No, stall, because stage is busy only, stall on, this is stall, busy here. So can I use execution stage? Yes, you can use execution stage. Why? See now, end of the execution stage, results is available. You can forward here. Forward. For addition, execution stage is required 1 clock cycle. 1 clock only. Addition required 1 clock. Now here is one stall. One stall. Then you can perform the write back. So clock number 8. Now similarly, go with instruction I4. That is what? Multiplication. So now see. All of you understand? So instruction fetch, instruction decode I can do. So can I execute? No, stage is not available. So this is stalls happen. Can I use this execution stage? Yes, you can use it. You can forward this one. Data you can forward here only. You can forward, right? Because then execution for multiplication take how many clock cycle? 2 clock cycles. Now here is what? Memory access. Here is memory access followed by write back. So clock number 9, clock number 10. Then do the analysis, then tell me the how many clock cycle. So now clock cycle, see, first instruction taken 5 clocks. Instruction I1. I'll mark it here, I'll mark it. The first instruction taken 5 clocks. Yes or no? 5 only? 5 clocks. Then after that, first instruction taken I clocks. Second instruction is the multiplication taken extra 2. Extra 2 only? Extra 2. Third instruction I3 is addition taken 1 clock extra. Instruction I4 taken how many extra? I4 taken 2 clocks extra because it's as a multiplication. So similarly, I can mark it, I5 will take 1 extra, I6 will take 2 extra, right? Yes or no? Then I7 will take 1 clock, I8 will take 2 clocks. Now count it, 5 plus 2, 7, 8, 10, 11, 13, 14, 16, yes. So 16 clock cycles happen. How many? 16 clock cycle happen. So time clocks operand forwarding mechanism, if you use 16 clocks happen. What is speed of factor? Speed of factor is time or number of clock cycles. But are they given any stage delays? Are they given any stage delays here? Are they given any stage delays? No, in terms of clocks only we need to calculate, right? In terms of clocks only we need to calculate. Time with, so without operand forwarding divided by, so time with operand forwarding will be, so this is 30 by 16. So 30 by 16, how much value it will be? 15 by 8. This how much gives? So up to what decimal? 2 decimal they said? Up to 2 decimal they said? So 30 by 16 is giving 1.87. So 1.87. So 1.87 is the right answer for this question, ma'am. I hope you understand. Easy. If you are willing to take the tabular diagram also, what you can do here, instead of drawing the diagram, so number of instruction, how many? 8. Addition, multiplication. So now row, you just add instruction. Stages, how many? 5 stages. Plot the what? Number of clocks. All stages taking for all instruction 1 clock except execution stage. Execution stage, addition take 1 clock, multiplication taken 2 clock. That column only updated. Then I is given how to update row and column. Row means what? Add. Row you add, column also add. Then remaining cells, maximum of the 2 cells you can do it. I given that shortcut approach that you can apply. That also will give the 16 clocks. So then you can answer it. I hope you understand. Chalo, we'll move to another question. We'll to another question here. Look at the question. This was asked in GATE 2017 paper, set number 1 for 2 marks. Instruction execution of processor divided into 5 stages. 5 stages. Instruction fetch, instruction decode, operand fetch, execution, write back. The stage the latency is also given 5, 4, 20, 10, 3 nanoseconds respectively. A pipeline implementation of the processor required buffering between the each pair of consecutive stages with a delay of 2 nanoseconds. Register delay given. 2 pipeline implementation of the processor are contemplated. That is a naive pipeline implements, that is NP with 5 stages, and another one efficient pipeline EP where operand fetch stage is divided into 2 stages, YF1 and YF2 with execution times are 12 and 8 nanoseconds respectively. Then the speed of correct to 2 decimal places achieved by EP over NP for executing in 20 independent instructions with no hazards. Again see, so it is similar to previous one question, right? Yes or no? This is the previous like 12th question, this is common. So the some stage divided into multiple stages here. Now they are asking again, if I want to run, if I want 20 instruction in the 2 pipelines, what is the speed of factor only they are asking. Okay. So let's note it. What are the stages? 5 stages they said. 5 stage instruction pipeline. What are the 5 stages are there? What are the 5 stages? Instruction fetch, instruction decode, operand fetch, execute, perform operation they mention. Perform operation, memory access and write back. Correct? 1, 2, 3, 4, 5. Sorry, 6 or 5 stages. Let me read it again. 5 stages, instruction fetch, instruction decode, operand fetch, execute, write back. Memory is not there. So memory is not there. Write back only. Okay. What are the stage delays? Stage delays are 5, 4, 20, 10, 3. 5, 4, 5, 4, 20, 3, 20, 5, 4, 20, 10 and 3. 10 and 3. 10 nanoseconds. This is 3 nanoseconds. All are in nanosecond stage delays. Okay. Now this is a 5 stage instruction pipeline which we have. Now this instruction pipeline, what they did, so instruction fetch as it is, instruction decode as it is, operand fetch made it into two things, operand fetch 1 and fetch 2. Then perform operation, write back will be there. What is stage delays? They said 5 nanosecond, 4 nanosecond, this is what 12 nanosecond one is, another is 8 nanosecond, this is 10 nanosecond, this is 3 nanoseconds. I hope you are marking. This is what 5 nanosecond, this is 4 nanosecond, this is 12 nanoseconds, this is 8 nanosecond, this is 10 nanosecond, which we already know, this is 3 nanoseconds. Okay, how many stages happen? 6 stages happen now. Stage is 6 here, 5. This is 6 stage instruction pipeline. What is the name of the pipeline? I can mark it. So this is what NP pipeline. This is what EP pipeline. So EP pipeline. So this new design. So they are running how many instructions? They are running how many instructions? 20 instructions. 20 instructions they are running. They are asking speed of factor. That's it. So what can be done? What can be done? Suppose time for NP, I am taking NP. First of all, how many instructions we are running? Are they given any branch instruction something? No, no dependency, no other hazards they said, no other hazards. So how to get the pipeline time for executing 120 some number of instructions? So we know, right, K plus N minus 1 into TP. What is TP? Cycle time of the pipeline. What is the K? 5 stages. How many instructions running? 20. So 19. So how to get the TP value? Maximum stage delay, right? What is the maximum stage delay? 20 nanosecond. Are they given register buffer overhead? Are they given register buffer overhead? They said no, delay is 2 nanosecond. Yes, simple. So now TP is what? 20 plus 2, 22 nanoseconds or not? So this is going to be 24. 24 into 22 nanosecond. I hope you understand. Here, what is the formula I am using here? 20 instructions I want to run in pipeline. So first instruction will take how many? K stages, K clocks required or not? After that, each instruction will take one clock only. Yes or no? 20 instruction when you run in a pipeline, first instruction has to go all the stages, 5 clocks required. Remaining n minus instruction will take one clock only, which we discussed. So 19 clock, 19 plus 4, 24 clocks. And pipeline time is what? Each stage delays are different. Maximum stage delay you have to take it. So 20 buffer also there. So 22 nanosecond. So this you can do it. Now time for efficient pipeline equal to K plus N minus 1 into again TP. What is the K? Here 6 stages. So 19. What is the stage delay here? What is the maximum stage delay? In this case is 12 nanosecond. 12 plus 2, 14 nanoseconds. So this is going to 14 nanosecond. This is 25 into the 14 nanosecond. Yes, what is the value? So what values it is giving? You can comment. So 24 into 22. What is the value? 528. This is 528. Now, so this is 528 divided by 25 into 14. 350. So now 528. This is 350. Okay. What they are asking here? What they are asking here? What they are asking? Speed of factor. Speed of factor. What? They said na EP over NP. So now should I write N time for EP by NP or NP by EP? You should write NP by EP. Ma. Please do not confuse. Because we are preferring EP over NP. We want to prefer EP over NP. So time NP by EP. So this time is 528 by 350. Right? Yes or no? 528 only. So this value gives how much? 528 divided by 350 giving 1.50. Sorry, 1.50. Range would be, so 1.50 to 1.51. So this way we can answer the questions now. Yes, I hope you understand. The entire pipeline concepts we have completed, ma'am. See, almost 5 parts I have taken, means more than, so like each is more than 1 hour I have taken, almost around I can say 6.5 hours we have spent on instruction pipeline. We started initially with the basics, their performances, finding the speed of factor, efficiency, throughput, those things we calculated with a good number of problems, followed by we have seen the performance of the instruction pipeline and hazards, what are the dependencies, that is data, control and structural. There are various problems, there are solutions, possible solutions I discussed, and possible problems on each area also discussed. And this entire, these 5 parts are very much important. So please you watch all the things, but definitely you are going to be benefited out of it. Clear? So again, so another session I'll come up with the IO part, so DMA control I'll discuss, some even floating point, already 2 sessions I've covered, I'll be covering that also. So weekly 2 days will be there, even I increase the number of sessions, I'll start even operating system in upcoming schedule. So we'll show the schedule also upcoming sessions, and also do not forget to attend the every day, like today's the 24th and the 24th at 4 p.m. we have a TOC classes also. The TOC classes planned like weekly 2 or 3 times, and OS also, COR OS planned 2 times. So do not miss the sessions. So get the advantage of it more. So not only computer science branches, even other branches parallelly going on. The main objective of this foundation course is the faculty will go basics levels. The basics level is the concerned topics, concerned subjects, so that this is definitely going to be useful to the student. Those who are willing to take the admission, like you can definitely approach, the number already scrolling down, right? If it is online mode, you can do it. Like if you are looking for physical classes, the physical classes available in Vijayawada as well as in the Bangalore Jayanagar Center. So definitely you can go visit the centers for admission. Thank you so much.